Hello students, welcome to the online class of physics, solid state physics, which comes under your paper 6A in your semester 5. We are dealing in unit 4. I am N. Chandana, assistant professor of physics from Government Degree College, Khairabad, Hyderabad. Let us have a quick recap on the previous class, what we have done. We have done superconductivity. What is superconductivity? The phenomena in which the resistance of a given material becomes zero at a particular temperature. What did Kamerlingh-Onnes do? Kamerlingh-Onnes have done experiment on this mercury, and he has obtained that the resistance of mercury becomes zero at a 4.2 Kelvin temperature. Okay, that means the resistance has become zero. It has become it has reached a state called a superconducting state. This phenomenon is called superconductivity. Okay, this was invented by Kamerlingh-Onnes in 1911. Right now, based on this and this temperature, at this temperature, it got uh, resistance become zero, and below these temperatures, we obtain superconducting nature. Once I exceed this 4.2 Kelvin, again I will go for normal state of mercury. Normal state of mercury. This was given by Kamerlingh-Onnes, and this is a definition. Okay. Then we have basic experimental facts, like what all the experiments they have done, and based on that, what all the facts we have come up. They are at room temperature. Superconducting materials have greater resistivity than when they are in materialistic form. Greater resistance will be more when they are in superconducting state than that of superconductible materials have greater resistivity than that of other elements, right? Then similarly, I have already told you that for different isotopes, the critical temperature Tc will be different. Okay, and it increases with atomic weight. I have told you with atomic weight. And the superconducting property is not lost by adding impurities. That you have to remember. It's not lost by adding impurities. Okay, and also there is no change in the crystal structure. There is no change in the crystal structure. Okay, which was given by X-ray diffraction. Okay, given by X-ray diffraction. Now next, we have done the superconductivity and zero resistance, right? Done this superconductivity and zero resistance. How do we attain zero resistance? You consider a ordinary metal. We know that in ordinary metal, why do we have a? If you consider an ordinary metal, why do we have a resistance in an ordinary metal? This is because the collisions made by whom? Collisions made by the conducting electrons with the lattice ions of the crystal. Lattice ions of the crystal. Okay, conducting electrons with the lattice ions of the crystal. Then we have resistance developed inside the material. Resistance. Okay, now what happens in the superconducting state? These electrons will form pairs, nearby electrons, by exchanging some force between these among these two electrons, and from this and this way, exchanging force between these two side by side electrons, and they'll form a electron pairs will form some electrons bound system. Okay, electron bound system, so which never exchanges any energy with the lattice ions. This electron bound system will alone moves when we apply some external electric field to the superconducting material. Then what happens? Maximum current will flow. Okay. Now there won't be any energy transfer from this system to the lattice ions. Hence, what happens? Now this moment will result in maximum kinetic energy or maximum velocity or maximum current. Hence the resistance is 0. The resistance will be 0. That means it achieves superconducting state. Superconducting state. Okay. Now next we have today I'm going to teach you the effect of external magnetic field to you all. Okay, let me share whiteboard. What is effect of? Talk about that. Second, effect of external magnetic field. External magnetic field. Effect of external magnetic field. What is happening? See, you have a superconducting material. Now we want to bring back that superconducting material into normal state. Into normal state or normal material. Okay. Then what we have to do is directly we will apply some external magnetic field. External magnetic field. Okay. This destroys the superconducting property. Superconducting property of the material. When we apply some external magnetic field to the superconducting material, then the magnetic superconducting material becomes again normal material having what? Normal resistance. Okay. So this is obtained when a strong magnetic field is applied to a superconducting material. This field, this minimum field which is required to destroy the superconducting nature, or which is to restore the normal resistance. This minimum field, magnetic field, is called critical magnetic field. Okay, it's called critical magnetic field, which is nothing but the minimum magnetic field required for a superconducting material to get back to its normal state. That is, retain the same resistance what it has in the starting position. Then that is called critical magnetic field, Hc of 0. Hc of 0. It is denoted by Hc of 0. So the minimum value of applied magnetic field, when the superconductor, what happens? It loses the destroys the superconductivity, this magnetic field, or get back to its normal resistance mode. It's called critical magnetic field. Okay. Now, if the applied magnetic exceeds Hc0, then what happens? The superconducting state is destroyed. It destroys the superconducting state. Okay. Similarly, when we have, I told you already that the critical value of the temperature of the specimen is raised above the critical temperature. Again, above critical temperature also, the magnet behaves as a normal state. That means normal resistance it has. Above critical field, magnetic field also, it has normal materialistic state. But only when it is less than Tc, critical temperature, it exhibits superconducting state, and less than Hc naught, it exhibits superconducting state. Okay. Now we can say that superconducting state can be a can exist, right? What I have told you is superconducting state. What I want to tell is superconducting exist when it has a temperature should be more than Tc, and also magnetic field applied should be more than Hc. Oh, that is critical magnetic field and critical temperature. Then only we say that the material exhibits superconducting state. Okay. Now we have this equation. I'll write here one second. What is that? That Hc of T at a particular temperature will be equal to critical magnetic field into 1 minus T square by Tc square. So at a particular temperature, what is the critical field required will be equal to the critical magnetic field minus T by critical temperature, Tc. T square 1 minus T square by Tc square. Okay, so at a temperature T, the maximum field strength applied is Hc of T, and at absolute zero, this is at absolute zero. At absolute zero Kelvin, what is the applied magnetic field? Okay, critical field or critical field is Hc of 0. And what is Tc? It is the critical temperature, right? The if Tc is very much high, then obviously Hc of 0 will be also high. Both are proportional to each other, right? Now let us do one small problem. Okay, given the transition temperature for lead, for Pb, the transition temperature is given, right? Tc is 7.26 Kelvin. Okay, the maximum critical field for the material, maximum critical field means Hc of T, right? 8 into 10 power 5. So lead has to be used as superconductor subject to the magnetic field of 4 into 10 power 4. Okay, then what should be taken, what precaution should be taken to make my lead to be as a superconductor? This is Hc. Okay, Hc of 0 at 0 Kelvin, 8 into 10. Tc is 7.26 for lead, and also given Hc of T is 4 into 10 power 4 ampere per meter. Okay, what precaution will have to be taken such that the lead is used as a superconductor? Okay, so that's the reason. So what will I do? I'll directly write T is equal to Tc into 1 minus Hc of T by Hc of 0 whole power 1 by 2. See, from this formula I have written this. See here what happens. Hc of T by Hc of 0 equal to 1 minus T square by Tc square. Okay, now what happens now? T is equal to, now Hc of, I'll remove this 1 here. Okay, so 1 minus Hc of T by Hc of 0 equal to T square by Tc square. Okay, now what happens? T by Tc equal to root 1 minus Hc of T by Hc of 0, right? So what happens to T now? T equal to Tc into 1 minus Hc of T by Hc of 0 whole power half, right? This is the temperature which we are required. Now what will be T now? Tell me, students. Tc is 7.26. Second. So 7.26 into 1 minus 4 into 10 power 4 by 8 into 10 power 5, right? Whole power half. 7, 6 into 1, 10. 20, 20 minus 1, 19 by 20 whole power half. Okay, this is approximately equal to 7.5 7.1 Kelvin. This is the temperature at which maximum magnetic field will be there, critical magnetic field, at which the lead behaves as a superconducting material. Okay, students. So this is one of the problems. Next we'll do this one. See, one more problem we'll do. A superconductor material has critical temperature given 3.7 Kelvin in zero magnetic field. Okay. Of magnetic field 0.306 Tesla at 0 Kelvin. Find the critical field Hc of T at 2 Kelvin. Okay, so this is T. Hc of T we have to find out. We know that Hc of T is equal to Hc of 0 into 1 minus T square by Tc square. Right? What is Hc of 0? 0.306 into 1 minus, what is T square? It is 4 by, what is Tc square? 3.7 whole square. Right, finally I'll get in the terms of 0.0218 Tesla. This is nothing but the critical field at 2 Kelvin. Okay, students. So this is the way we use this formula to determine the critical magnetic field. Okay. Next, let us go for Misner effect. Misner effect. Okay, or this is also called as flux exclusion. Called as flux exclusion. Okay. So what is Misner effect? See, in 1933, Misner has given this phenomena. What is that is when a superconductor, if you take a superconductor, it is very much cooled in a magnetic field. So you're applying a magnetic field, and simultaneously cooling the superconducting material below critical temperature. Below critical temperature, then what happens below critical temperature? It exhibits superconducting state below critical temperature, no? So when we apply external magnetic field and we are reducing the temperature below the critical temperature, cooling, then what happens is I have a superconducting material in this way. Now my magnetic field is in this way, from downward to upward direction, B bar. Okay. Now what's happening is after some below critical temperatures, less than critical temperature, if I am cooling that field in applied magnetic field, this semiconductor, then what happens? The lines of force, magnetic lines of force, that is, the magnetic flux will come out of this in this way. They won't enter the superconducting material anymore. They have come out, expelled out. Okay, so the magnetic lines of force will expel out and get expelled out when I have a superconducting material which is cooled below the critical temperatures, in an applied magnetic field. Okay, this phenomenon is called Misner effect. So take a superconducting material, cool it below the critical field uh, under applied magnetic field, then this is called Misner effect. Okay, now this is a superconducting material in normal field, normal state. Okay, now when I cool the specimen below the critical temperature, then what's happening? The magnetic lines of force are coming out of expelled out of this material. So this is called Misner effect. Okay, Misner effect is always reversible. You should remember this. It is always reversible. Means Again we can get our material to the normal state. When we heat it again, that means when we remove the cooling process, then again it becomes into the normal state. Okay, that means Misner effect can be is reversible. Okay, now that means when temperature is increased greater than Tc, then this can be reversed. This effect can be reversed. Okay. Similarly, a superconductor is always a perfect diamagnetic, right? Perfect diamagnetic. Superconductor is always a perfect diamagnetic. The magnetic field induction V bar in a superconductor is always zero. The magnetic field induction in a superconductor is always equal to zero. Okay, this is also can be given by the Misner effect. Okay, this is Misner effect. Now we'll go for critical current value also. So the maximum current that can be passed in a superconductor without destroying superconductivity. So what is critical current? As we all learned, critical temperature, critical field now. Now we are going for critical current. Critical current density. Current density is nothing but current per unit area. Right? So I'm going for current density. Critical current density, critical field, critical temperature, right? So the maximum current that can be passed in a superconductor without destroying the superconductivity is called critical current. Critical current, okay, denoted by IC, and the current density is denoted by JC. Okay, see below this the below this current, the material behaves as a superconducting material. Okay, but above this, like slightly above or equal to this temperature, what happens? This current, what happens at this point? The superconducting material loses its superconducting state. It becomes again normal. This is called critical current. Critical current. Okay, and the critical magnetic field and critical temperature. So all these things can be represented in a diagram. Second. So they can be represented in this diagram which is relating critical current, critical field and critical magnetic field. Okay, this is current density G, and this is H, critical magnetic field, and this is critical temperature Tc. Okay, so Jc is there when T is equal to 0 Kelvin or H equal to 0, and here H is, this is the point where, tell me, T equal to 0 and G equal to 0, right? Similarly, this is the point where J equal to 0 and equal to 0. So this is the, till here this is a superconducting material. Here this is a superconducting material. When we exceed Hc, then it is a normal material. When we exceed Tc, this is a normal material. When we exceed Jc, this is a normal material. Okay. This is called phase diagram. Okay. Phase diagram. Okay. Material is a force phase diagram of a superconductor. Now beyond this Jc or beyond this Hc or beyond this Tc, the material behaves as normal state. This is superconducting state. Okay. This is normal. This is normal. Okay, normal state. Right. Now let us see. So this is a normal state and this is phase diagram. So you can say that HC, DC, and IJC, current density, or IC, current, critical current. On these three factors, our superconducting state depends. When we exceed any of these limits, the state becomes normal state. Okay, students. So let me go for a revision. Next class, we'll deal about type 1 and type 2 superconductors. Okay, external field, Misner effect, and critical currents we have seen. Okay, we have done problems also. So next class, we'll deal about type 1 and type 2 superconducting materials. Conductors, their applications. There is one theory, BCS theory. We'll deal what is that theory, we'll learn. Okay, students. Thank you so much for your patient listening. Thank you.